Maybe you can get started. So, hi guys, thank you for being back after the coffee break. So we have a very exciting talk. So our speaker is a senior fellow, very distinguished personality from Intel, Dr. Debendra Das Sharma. So he wears multiple hats. He's also one of the key persons behind the PCI Express, CXL forum. So again, due to lack of time, without further ado, let me yield the floor to a distinguished speaker, and let's welcome him.
Right. Thank you, Hari. All right, so I'll talk about Compute Express Link and how we are building with this open interconnect composable systems. So quickly, agenda-wise, Load-Store IO in the compute landscape. Then we'll talk about CXL and how it has evolved, and then conclude. So I'm not going to spend a lot of time here in the initial parts, but basically the explosion of data with the data-centric revolution is causing a lot of interesting challenges and a lot of opportunities, right? The drivers are the usual ones: cloud, 5G, lots of IoT devices, automotive, all of them. And with that comes scaling challenges, which is, latency, bandwidth, capacity, they're all important. So fundamentally, you have to move the data faster, process everything that you are getting, and also do this securely, seamlessly, and efficiently. So this is the compute landscape today. Typically you have racks of servers, right? Pods of servers, huge numbers of them, and basically within each rack you've got several drawers or chassis, right? And each of them is a server, and they have their own resources, memory, IO, whether it is accelerators like GPU, FPGA. You'll have a NIC having some kind of a networking connection to the top of the rack switch, and then beyond that, the racks are all connected through some kind of a networking fabric. Short distances are copper, longer distances are optical. That's really what the data center looks like today. And the challenges with all of this is that how do you treat the data center as a computer, right? And earlier speakers have talked about how resources are being fragmented, how they are being held captive at each and every node. For example, memory that belongs to a particular server cannot be used by another server. Let's say I got 5 terabytes of memory in one server, and in each of the servers, and one server needs 10 terabytes. It cannot really go and borrow the memory resources from the other servers by using the load store semantics. So those are the types of challenges that we need to solve in order to address all the opportunities and challenges that exist with the huge amount of data that we have to process. In this context, let's look into what is the basis of all of these load store kind of interconnect, and it is basically PCI Express. It has it has become the ubiquitous IO, not just for IO kind of connectivity, but also for CPU to CPU cache coherency protocol, symmetric multiprocessing protocols. They're all based on PCI PHY, because why would you invest your time in designing unique PHYs, right? When you get something that's moving at a pretty rapid pace in terms of increasing in terms of its bandwidth capability, right? So PCI Express doubles the data rate every generation, roughly on an average 3 years, right? So on the right side, you will see the different versions of PCI Express specification. I've been fortunate to work with PCI Express since the day one. I've seen it evolve and have helped it safe evolve. We started off with 2.5 gig, 8-bit NV encoding. So if you take a by 16 link, your bandwidth per direction is 32 gigabit per second, and you can go down that table. Gen 2, we increased it to 5 gig, but you look at Gen 3, we did 8 gig, and yet it is a doubling of the bandwidth because we changed the encoding scheme. And that's fundamentally what PCI Express is all about. It basically looks at the entire ecosystem, everything from your PC, handheld, workstation, server, cloud, HPC, everything. And it says that, what can we do so that people can design to the same standard, right? You don't want to leave anybody behind and say, hey, solution 1 for you, solution 2 for you, and solution 3 for you, right? Instead of that, what we said at that time was that, hey, we could not go to 10 gig without either blowing up the cost or blowing up the power. So what we did was we said, let's go to 8 gig, it's 60% more. But what we want to do is that we will change the encoding scheme. It's logic, so fine, we'll deal with that, right? So that's how we went with 128B, 130B. After that, the materials and everything kept up. So, and pretty much, the channel length hasn't changed, from Gen 4 days, right? 16 gig, 32 gig, and then with Gen 6 was another major transition. We went with PAM4 signaling, 64 gigabit per second. So you get a terabit per second of bandwidth per direction, right? And that was in 2022. And then 7.0, which is work in progress, expected completion in 2025, 128 gigabit per second per lane, right? So different widths are there for different usages. And the fundamental thing is it's fully backward compatible. You buy a Gen 5 based system today, like an Intel Sapphire Rapid, you have a Gen 1 card from 2 decades back, you plug it in, it works, right? So, and the drivers for all of these are, of course, the usual suspects, your networking, XPUs, memory, alternate protocol, CXL, which we will talk about. And then it basically keeps on supporting all of this. The other fundamental thing is it's low latency. And if even through all of these transitions, if you look into our symmetric multiprocessing cache coherency protocols, latency has been flat for more than a decade now, right? So, pretty impressive from that point of view. And it's by design, it's by necessity, right? So now let's talk about, in that context, why do we need a new class of interconnect, which is CXL? Well, with PCIe today, the picture on the top represents the worldview that we have today, with PCIe, which is that it's a load-store interconnect, but it is non-coherent. And by that, what we mean is, yes, you get direct access to memory, but you get that access non-coherently. You cannot cache the memory content inside the devices. And if the device has memory, it cannot be really cached in the CPU either. It's all non-coherent space. And that's fine. That really works well for the large class of IO so far. But then the challenges with that model is that we got 4 sets of challenges that CXL is trying to address. I'll go through them one by one. The first has to deal with heterogeneous computing, which needs finer grain sharing of data. So that's one thing. The second thing is the challenge around memory bandwidth and memory capacity. And people have talked about that. So heterogeneous computing means that, sometimes it's very inefficient, especially for a lot of these kind of compute with AI and ML, to move entire data structures back and forth between the CPU and then the device, right? And then keep moving everything at a larger granularity. So you want it to be able to, move data as if you're caching. With caching, what happens is you only get the data that you really need. And data can reside closer to where it is getting used the most, right? So you can make all of those kind of decisions. So that's the first problem. Second problem is around the memory wall. And there are 2 issues with this. If you look into the speed at which DDR is increasing its frequency, right? Right now, DDR5 is 5600 going to 6400. Now let's look into that, right? There are about 300 signal pins per DDR channel. So if you run at 6400, the bandwidth that you get is about 50 gigabytes per second, give or take, okay? If you look into a PCI Express, on the other hand, by 16, let's say if it's running at 32 gig, which is widely available today, your bandwidth is 256 gigabyte per second in both the directions, if I did my math correctly. So you get about a 5:1 per pin efficiency, and by 16 is 32 times 2, which is 64 lanes is what you have, right, between transmitter and receive pin. So you basically have a huge delta in terms of per pin bandwidth. Now the downside is, of course, higher latency, because SerDes fundamentally has more latency than a parallel bus. But the parallel bus cannot keep on increasing. If you look into the way we are dealing with this bandwidth challenge is by adding more and more and more channel, DDR channels on the CPU. Right now, we started off with a single DDR bus, then it became 2, then it became 4, then 6, then 8. on and on and on it goes, and each one of them is 300 pins. So it's a huge amount of cost adder in the system. Also putting those memory very close to the CPU, because it's a parallel bus, causes thermal challenges in terms of cooling and things like that. So that's where we need to solve the problem. The other problem with memory has been that the price per DRAM per gigabit has flattened out. As you're adding more and more cores, that means you add more memory capacity into the system, and fundamentally that causes an increase in the price of that memory that you're adding into the system. So those are the two sets of problems. I'll talk about the other ones which people have talked about as we go through the separate generations, subsequent generations of CXL. So CXL was basically started off trying to address these first two sets of problems. So with that, we'll quickly go through CXL. So fundamental approach of CXL is that it's a coherent interface built on top of PCI Express. Do not want to reinvent the wheel, right? You want to use PCI Express PHY, you want to use PCI Express device discovery, DMA move engines, all of those things you want to reuse. Notification, all of those things, software has been defined. So you want to make use of all of those. You don't want to reinvent the wheel. People that try to reinvent the wheel just end up spending their energy in reinventing the wheel, right? Just added two more protocols: caching, very simple set of caching protocol, and memory semantics on top of what exists. So that's what CXL is. It's three protocols. .io is basically PCI Express. .cache is caching protocols, which is messy protocol based. And third one is memory. Low latency. Anytime you are having memory or somebody that has a caching agent, you want that latency to be really low. How low? Well, it should be equivalent to a NUMA hop latency. So in other words, if I'm going to a neighboring CPU today using Intel's, let's say, QPI link, the latency that I get, I should be able to get the same latency on the device side because it's using the same PHY. Right? So if you did things properly, you should be able to get that kind of latency, and we know how to deal with that latency. So clearly there is a difference. If you are accessing a local DDR, your latency, idle latency is 100 nanoseconds. I'm giving round numbers here without getting into a lot of the details. If you access a memory that's in the neighboring CPU, 200 nanoseconds, right? So that's basically the ballpark in which you are looking at. Third aspect, it's an important aspect, has to do with asymmetric complexity. Symmetric cache coherency protocols are hard. They change over time. I have done symmetric cache coherency protocol for 2 decades. I've tried to enable other people that want to sit on our QPI bus. Invariably, unless they're doing a node controller, they say, it's too hard, we're not going to do it. It changes over time. And it's not just us. I've looked at across the industry. It keeps changing. It's so tied to the fundamental microarchitecture, right, that it's hard to do. So CXL, early on, we decided that the home agent functionality needs to be whatever is your microarchitecture. And you can change it 20 times over the lifetime, doesn't matter. What exists on the device side is caching with a simple set of about a dozen instructions like read, share, right? Snoop, give a response, write back, in things that do not change, right? So that's basically what it is based on. And the first set of usages are direct connect for the first generation of CXL. So we define 3 types of devices, and as engineers, it's as boring of a nomenclature as you can get: type 1 device, type 2 device, and type 3 device. Okay, couldn't come up with anything better. So type 1 is basically, and type 2 are accelerators. The only difference is that type 2 devices have memory that they want to map into the system memory space as coherent devices. So, type 1 devices have .io and .cache. Examples can be SmartNIC. You basically want to cache the system memory. Type 2 devices, on the other hand, it's got much more finer grained processing you are doing. So dense computation, GPU, FPGA. So you've got all 3 protocols built in: .io, .cache, and .memory. Type 3, which is very interesting, and personally, I've started working on IAL, which we donated as CXL. We in this context means Intel. Never thought that this would take off, but guess what? This is the first one that people got very excited about, right? Memory buffers. Why? Because of the memory wall problem. So this one has got just memory bandwidth expansion and memory capacity expansion. The other interesting thing about CXL is that it's agnostic to the type of memory technology that you have. CPUs, if you have, let's say, DDR5, 6400, then all the DIMMs need to be of that type. in CXL, you can have mix and match. It works fine, right? The memory controller is on the buffer side. And by the way, that memory controller on the memory buffer, it doesn't really need to understand how to orchestrate cache coherency protocols. So that's why CXL.cache is not there. Even though it's cacheable memory, let the host deal with it, right? It knows how to deal with cache coherency. It knows how to deal with conflicts and all of that. Let it deal with it. As a device provider, all that you do is you provide, high bandwidth, low latency access. That's all. So that's CXL1. Now, what happened with CXL2 is coming to the third problem statement, which is stranded resources. And remember the problem I said that if I have 5 terabytes of memory in each and every one of my server, and I need the next few extra terabytes, I really cannot get it today, right? My only choice is I will have a lot of page misses. Okay. So here we introduced this notion of switching. Switch is optional. You can have multi-headed kind of devices, but fundamental idea is that you can have devices that can be pooled across a host of servers. So on the top, what you see, H1, H2, H3, all of those things are different independent servers, and they're connected through CXL link, and there is a switch, and these devices belong. So, the idea is that you can hot remove or hot add them. You're not physically removing, it's just a hot plug flow that you're going through. So you can assign this device to this host for now, and later on, when that, if it is done with it, you can assign to somebody else. So the basic idea is as follows, right? If I need an extra 5 terabytes of memory, I come to the pool, I say, hey, do you have 5 terabytes available? We'll say, okay, fine. I'm going to give you this 5 terabytes from this device, and it gets assigned to it. Once I'm done with that, I say, I don't need it anymore, and it's back on the pool again, right? So that's the basic idea. What's the downside? Well, the downside is that if you have a switch, you go through an extra hop, which is 50 nanoseconds, okay? But if you have a multi-headed device, it's almost free. It's the same as your CXL direct connect memory. So we allow for those kind of things. We also allow for persistence flow for the new types of memories that are coming up. And we define Fabric Manager to manage these resources and all of those things. So CXL2 was a fundamental shift in the load store paradigm, in the sense that for the first time you have devices that are being pooled across multiple servers, and devices have to understand the notion of these multiple servers. And that is possible because, if you look into PCI Express, we had done the homework way before for effectively assigning a device across multiple VMs. The same concept exists. The same concept gets leveraged here. The devices, multiple virtual functions are assigned to each of the hosts that they are assigned to, but the physical function is with the Fabric Manager. So that way the host thinks it has the full device, but it really doesn't control it. It gets the illusion, just like the VMs get the illusion that they control the device. The host gets the illusion that it controls the device. In reality, it is just controlling a virtual function and a part of the resource that is there. How am I doing? So CXL to address that third thing, which is which was devices or resources that were held captive, right? So you allowed for pooling. So what did we do with CXL3? CXL3 basically enhanced that notion of pooling even more, which was the challenge number 3. Challenge number 2 was memory challenge. So the other aspect within challenge number 2 was, I think, somebody was mentioning that a memory device you cannot do really near memory processing, because you are not part of the coherency domain. You just don't know whether the data that you have in the memory is the latest and the greatest. So CXL3 solved that issue, along with it also takes into account, because of the larger systems that we have, we allow for finer grained sharing of data across large-scale distributed systems. And I will go through this one by one. So you can read through this industry trends here, effectively, that those are the problem statements. And what we did with CXL3 was, first thing, we doubled the bandwidth, because PCIe 6.0 went for 64 gig. So we went with 64 gig on the CXL side. That is, again, right? I mean, no need for us to stay behind in the bandwidth curve. We are using the same PHY and the same infrastructure. We also introduced Fabric capabilities. This is an important thing because so far, all of these load-store interconnects are based on a hierarchical tree topology. With Fabric, you break across those restrictions, and we'll talk about that. And then it allows us to do this composable systems as a result of that, and then improved capability for better scalability and resource management while being, again, fully backwards compatible, right? One of the things we have learned, full backwards compatibility is our friend, right? It helps us going forward. So doubling bandwidth, I'm not going to go through this in a lot of detail, but fundamentally, it's a flit-based mechanism. CXL already had a flit-based mechanism. PCI went with a flit-based mechanism. So it's a 256-byte flit. There are transaction layer packets, which are basically transactions. These are the DLP stands for data link layer packets. So things like credits and those kind of things that you need. So those things, 8-byte CRC and then a 6-byte forward error correction. And that works well because it's about a 2 nanosecond latency adder with this flit, but with CXL, we can take no latency hits. So what we did was, we of course use the same mechanism for 256 bytes, but in addition, we have this little enhancement where we take that same CRC, it's 6 bytes of that CRC, and this CRC protects this part, and that CRC protects the other part. So the basic idea is that you get the data first half, and if it passes CRC, you consume it. So that way your latency is flat with respect to the previous generation. If it fails CRC, then you wait for the next set, you apply the forward error correction, then do the check. And if it passes, it passes. If it fails, you go for a link level reply. So that's fundamentally what it is. Two simple protocol enhancements we did, but they have huge impact in terms of how the future of this technology moves forward. The first has to do with unordered IO, and the second one is back invalidate. Very simple constructs, but profound impact. So what is the usage model? Multiple usage models are there, but let's give you an example here. Direct peer-to-peer access. Anytime it is a memory mapped IO like PCI Express, peer-to-peer goes directly, doesn't go through the CPU. If you are connected underneath the switch, it is a tree hierarchy, but still you would go through there directly. But if it is a memory that is mapped to the coherent address space, you really cannot go to the memory controller directly in the device side and access it, because again, you have no idea whether that data is the most recent data or not. The worst thing that can happen is the CPU or somebody else in the server has that data, for example, exclusive, and here you come and overwrite it, right? I mean, that's not allowed. You break coherency that way. So here, what we did was, first thing we did was, okay, we are going to have unordered IO, and then the other one is the back invalidate. I think I went with the back invalidate first, so let me complete that. So back invalidate, what it does is, it says that, well, you really don't need to manage coherency, but as a memory device, you have to track the directory. There are 2 bits of directory, and those are effectively, is the line being held by somebody, right? From directory state is, I. Is it shared by somebody or more than one entities, or is it potentially, exclusive, right? MESI, right? So you just look into those 2 bits and say, can I serve this request directly? If I cannot serve it, you just send a back invalidate from there to the host saying, hey, I got a request for this line. You tell me what to do. The host gets that back invalidate on the memory channel. It gives a response. It will, if it has the line exclusive, it's going to do a write back, or it is going to say, I don't have that line. Go ahead, do whatever you want to do, right? But either way, it's going to give you a response. Once you get the response, you know that the line state is clear. Then you can go ahead and service that particular line. So that's back invalidate. Unordered IO, what it says is PCI Express, the .io model of CXL.io as PCI Express is based on what we call producer-consumer semantics. And what that means is that that's the fundamental ordering model. What it means is, if I do writes and then I post a flag saying those writes I've committed those writes because the writes are posted there. So that means they may not have reached that destination, but that flag needs to push all the writes forward. And the flag can be either a write by itself, it can also be a read completion that you're issuing, right? So it comes up with this set of ordering rules, which says that, hey, this cannot bypass that, that must bypass this, those kind of things in order to enforce those architectural ordering semantics, and that's fine. Except for that to work, it has to be a tree topology, because if you start taking arcs like this and your data and flag are in different locations, it doesn't work, right? So what unordered IO does is it says we will keep the producer consumer modeling intact, but what we are going to do is move that ordering point to the source. In other words, if you are the ones generating the writes, you need to make sure that those writes went to the destination before you posted the flag. So it's effectively you're pipelining everything, and writes get a completion. And the way we do that is we say, hey, unlike writes that are posted here, writes are no longer posted, right? So you generate the writes, you're going to get a completion. Once you get all the completion, then you know that you can now post the flag. So that's all that is there to it. But fundamentally what it does is it's a different flow control class. We use the same mechanism. All that we do is we say, hey, if it is unordered IO channel, don't apply any of the ordering rules. They can go in any order, right? So today the ordering rules are there as a gate, right? It's like, oh, this cannot bypass that cannot bypass this. If you say unordered IO, we just say that the gate doesn't exist, which is a very easy thing to implement in hardware, right? So now, but what happens is now I can have like parallel paths. I can have these devices connect to each other on this side separately, and it will still work. So these are the two constructs with very profound consequences. Now I'm going to skip over this. It goes through how that back invalidate does another thing, which is it enables devices to implement snoop filter, which is a scalable mechanism in which devices can start tracking what the rest of the system has, instead of implementing necessarily an entire directory. Pooling and sharing to a larger scale, but the other key important thing is the shared coherent memory in hardware, right? So today, none of the hosts, they know about each other. They all have their own separate address space. They are completely oblivious to each other, which is the way you want it to be, because they are all independent fault domains. But if you want to share like a shared data structure between different hosts, let's say you're working on some kind of instead of doing message passing, you want to have a shared buffer, right? That's hardware guaranteed cache coherent buffer space. You can do that with CXL 3.0. And the way it works is that even though the hosts don't know about each other, now these devices, given the fact that they are pooled across multiple hosts, they have a notion of which host has which memory. Now, all that they need to do is make sure that, hey, this is a coherent shared memory space, in which case they're going to track which hosts have it and just use the same back invalidate flow. And now what you have is a mechanism in which you can do shared coherent memory across multiple independent hosts when the hosts just do not know about each other from a hardware point of view. Clearly from a software point of view, they know that they're working with other hosts. So this is more of the same thing, talking about different levels of switching. So that's that part, right? That shared coherent, global coherent, coherent space, or the global fabric attached memory is another name that you will see, is the one that solves that challenge number 4, which is you want large distributed systems that can do finer grain sharing between them, right? When appropriate. And you can also use it for the message passing and all of those things using load store semantics. So fundamentally, with CXL 3.0, we are in the world of fabrics. And no longer a hierarchical tree topology. We are in the world of fabrics. So if you look at this, this is a very simple connection, right? But you can see that between any two source destination pairs, there are multiple paths, which is a no-no, absolute no-no in the hierarchical tree topology. So with unordered IO and combination of all of those things, we have made that one possible. And now it's truly you can have this large bisection bandwidth by having multiple paths between any two source destination pair. And going forward, we are looking forward to having better RAS story and all of those things with CXL. So CXL is a huge step forward, not because it's a lot of complicated things, but we have made changes in very strategic places. It's a set of very strategic small changes that we have done, but with huge strategic impacts. And the journey is just starting, right? Hardware, mainstream CPUs For example, our Intel Sapphire Rapid CPU has got CXL, right? Our competition also has CXL. Lots of companies are working on CXL, right? We have decades of innovation ahead. We'll of course have a lot of learning from this early hardware that we will incorporate, but huge interest in the ecosystem, wide-scale spread IP availability. We announced CXL consortium in 2019, and here we are 2023, right? About 4 years later, you got products out there. So it's off to a good start. And CXL 3.0, post CXL 3.0 development is in full swing. And so that's all that I have. I don't know how much time I have per question, but more than happy.
Unfortunately, we are out of time. Thank you for the fantastic talk.
Yeah.
Right. So in order to keep us on time, let's try to do questions offline. So I'd like to introduce our